Hello and welcome to this first Meet the Scientist session. I'm going to check first before I say anything else and make sure everyone can hear. So if you can hear me saying hello, just wave from your classroom. And we have Karen Long connected from the DLN as a producer. So Karen will be able to see who's waving. Okay, great. I see lots of students waving. It's so wonderful to be connected with you today. Yay. So Marilise, I don't know that your classroom is hearing us. I'm going to let Karen work through that with you. And Marilise, I sent you Karen's cell phone number. So, okay, looks like we're good. So if you have any challenges, you all have Karen Long's cell phone number, and that would be a good place to call. So let me go back and say hello again. I am Bonnie Murray, and sitting with me is Dr. Marilee Rule and Kristen Domadeo, and we'll go through a little bit more introductions in just a moment, but let me say that we are all connecting from NASA Langley Research Center here in Virginia. So we're over on the East Coast. If you think of going from north to south on the East Coast, the Chesapeake Bay is a pretty predominant feature along the East Coast. And we are right at the bottom of the Chesapeake Bay. So that's where NASA Langley Research Center is. And we're connecting from you to talk about SAGE 3. And SAGE 3 is a mission that's on the ISS. So we're all sitting in front of the ISS today, and that's our background. So wonderful to be connected with you all. The connection is being done as part of the work funded by NASA's Science Mission Directorate, and it is funded through one of the cooperative agreements that were awarded about 2 years ago, I guess that is now. And the particular agreement we're working with is Arctic and Earth Signs, S-I-G-N-S. So if you're interested, if you're watching the broadcast at some point and you want more information about this project as a whole, that's what you want to Google, NASA's Arctic and Earth Signs project. And they are working, that project is working with students and classrooms in Alaska on globe research. So they're using globe protocols. And if you want to know more about that, go to the website for Arctic and Earth Signs and you'll see it. And all of the classrooms there involved in this project are researching their environment through globe. And we are connecting the students in Alaska with NASA scientists today to help them to be able to understand how NASA does science and help them to see how they can be a part of that. So let me go through some more introductions, and I'm actually going to start with Kristen. Kristen Domadeo is the communications manager for the SAGE 3 project. So I've already told you we're going to talk to a scientist, and Dr. Rule will get to that part in just a moment. But there's more to all of the NASA missions than just the science. It has to be communicated as well. So tell us a little bit about that, Kristen.
Sure, Bonnie, thank you. So my job on SAGE 3 was to communicate all about the project, all about the mission, to everyone from the public, to stakeholders at our headquarters, to internal team members, and to people here at NASA Langley, and also to students like you and teachers. So I started back when the project was just getting started about 7 years ago, and I came up with a plan on how we wanted to communicate, and I then implemented that plan over the next 7 years, culminating with launch when we launched in February from Kennedy Space Center, and you'll hear more about that later. So a lot of people think of NASA and think of scientists and engineers, but our huge and diverse team of people included people like me and graphic artists and writers and educators who were able to help share the message of SAGE and share the science that we're doing with people all over the world.
Right, thank you, Kristen.
Thank you.
Yes, and I wanted to bring that out. But just by a show of hands at the schools, how many students in the classrooms like writing? I know as a child, I used to love to write. That was a few years ago, but I did. So let's see with hands, how many of you like to write and tell stories? Yeah, awesome. Okay, well, that is a big part of Kristen's job. So if that's something you have a passion for, there's a place for you at NASA. So think about that and think about that as possibly part of your future. So thank you, Kristen.
Thank you.
And we're going to move on now to Dr. Marilee Rule. And Marilee is here with us. She's going to be presenting to you information about the SAGE mission. Let me tell you a little bit of background. Marilee is a scientist here at NASA Langley Research Center. She works on the SAGE 3 project. In fact, she is the science manager for the SAGE 3 project. But she didn't get there without doing a lot of studying first. So in addition to the great work she did in middle school and high school, she went on to get a bachelor's and a master's from the University of Arizona, and then went on to get a PhD in atmospheric and Earth Science at Georgia Tech. Did I get all of that right?
Yes.
Yes, excellent. Okay, all right. I do want to give you, that's a lot of studying. How many of you students, let's do a little show of hands again, how many of you are interested in studying science? We asked how many are writers, and that can be both. You can have one hand for writing and another for science too. It doesn't have to be mutually exclusive. So interest in science, yay, that's wonderful. Great news. I'm delighted to hear that. And I'm sure you are as well,
I am too,
Marilee.
yes.
Yeah.
We need more scientists.
Right, right. There's a lot to study. Yeah.
Yes, there is.
So let's let the schools introduce themselves. So I know you're all muted. As we go across, I'll allow you time to just unmute, and Karen will help with that. And you can say hi to Dr. Rule, and then we'll get started with Dr. Rule's presentation. Okay, great. Marilee, we're sticking with that. Okay, so first of all, I want to say we have Caroline connected, Caroline Montgomery. Caroline works with me here at NASA Langley Research Center on another responsibility that I have, which is the STEAM project. And many of you connected know that I work on that project as well. STEAM is funded by MUREP at NASA, Minority University Research and Education Program. And STEAM studies Earth systems, technology, and energy education. So Caroline, say hi. We'll just let you introduce yourself.
Hello, everyone. Nice to be with you today. Bonnie pretty much said everything, so I'm glad to be here. Just listening in.
Awesome. So Caroline's going to be monitoring questions. I need to say also there's somewhat of a virtual audience. One of the teachers, Gina, is connected and watching. Hi, Gina. We can't see you, but I hope you can see us. Gina's home with her newborn baby. You maybe remember from the summer, teachers who were at the workshop, that Gina was expecting, and she had a little girl, and she's home watching the broadcast. Elena, who is the PI, the principal investigator for Arctic and Earth Science, is watching as well. So Elena and Gina, if you signed in with your Gmail address, you'll be able to submit questions in the chat. And Caroline's going to help with monitoring those questions. So thank you, Caroline. We'll be checking back with you. Okay, next classroom over, I believe we have Ms. Chastity Perez. Chastity, is that your classroom there? You can wave and say hi and unmute and say hi. There they are. All right. So big hello from Chastity.
The elder.
Let's hear you. Oh, and Chris is there with you. Hi, Chris.
Hi, Bonnie. Hi, Doctor.
Dr. Marilee. How about we go with that? Dr. Marilee. Well, hello to you all there. You're at North Star School, correct?
We're at Watershed Charter.
Oh, okay, thanks. I'm making a note because I'm going to call on you, so get ready.
All right.
Okay, all right, moving over. We next have Ms. Julie Selves at Dot Lake School. So Dot Lake, if you will unmute, give us a wave, say hi. Hi, Julie.
It's getting cold.
Yes, it is. Work? It is. Just say hi again. Give us a hello.
Hi.
Hello.
We have a school 10 across.
Say it again. Oh, they're muting. Okay.
We have another school in our district with this 10 across. So this is 2 schools actually, our whole schools.
Okay. Awesome. Thank you so much. That's great. That's me.
Hello.
Awesome. Okay, and then we have Ms. Marilee House is connected from Eagle Community School. If you want to unmute Marilee and say hi. There you are. Okay, we need a big hello. I can't hear you from Alaska, down here in Virginia.
Hi.
All right, good morning. All right, how about Tyler? I believe Mr. Tyler Ivanoff's class is connected. Tyler, you want to unmute and say hello?
We've got the Shishmaref seniors here. You guys want to say hi?
Hi.
Hello to Shishmaref. We're so glad you're connected. Great to have you with us. Awesome. All right, and then Sarah Lucas, I believe your class is connected as well from Tooksuk Bay, Nelson Island School. Did I get that right? There they are.
Wow, that's a lot.
Say hello. We need to hear you down here in Virginia. Okay, we're not hearing you, but we'll work on that, Karen. I'm sure you'll be able to help them and get that going as well. So, okay, so I know that you all are ready to take notes. So before I turn this over to Dr. Marilee, I think that's what we're going to go with. Marilee spells her name M-A-R-L-E-E. Oh, I'm sorry. It is M-A-R. Thank you. Let's get, why don't you tell them how to spell your name?
M-A-R-I-L-E-E.
There we go. Okay. And her name is on the bottom of the screen too, so that you can put it down in your notes, because I know they have a special sheet they're using notes for.
Cool.
Okay. And make sure that you're writing any questions that you have in that box for questions, any words that you may not be familiar with, so that as Dr. Marilee goes through her presentation, you can come back and ask her questions. And she may have some questions for you too, so be ready. So, all right. Without anything else to introduce, I think we're all connected now. I will turn it over to you, Dr. Marilee. Thanks. You're welcome.
So I'm Dr. Marilee Rule, and I started my career, my science career, probably when I was in junior high school, and just was interested in, all things that were kind of problem solving or science, and I think beekeeping was involved in that at one point.
Oh, that's interesting.
Yeah, because how bees make honey, and how you take care of them and the hive and stuff. But I just went through high school and college, also just math and science. I was really interested in math and science. And back when I was in high school, that was when Mount St. Helens erupted. And I think that really galvanized me as far as I'm really wanting to study science and what happens, with volcanoes, and then what happens to the atmosphere. And, just the whole event was probably a big milestone for me. So, and from there, I've just gone on studying, went into college. I went into engineering initially, electrical engineering, because I really liked math again, and got my degrees in engineering, electrical engineering, and that's what got me a job at NASA. And then, so I've worked on some amazing projects as an engineer, and then about middle of my career, I decided I wanted to go back into science, and I was allowed to go back and do my PhD at Georgia Tech, and that's in Earth and Atmospheric Science. So I'm officially a scientist now.
Yes,
so.
yes, that's right. Yes.
But it all started with just being interested in why things were the way they were, just trying to understand, how things worked in the world, I guess, and has led me to here. I love working at NASA. It's a great job. I love being the science manager for SAGE. We're in this really great time where we're getting real science from the atmosphere, from the instrument on the ISS, and I get to manage that project as well as understanding, just looking at the data, I guess, and understanding what is happening in our atmosphere. And when I'm not being a NASA scientist, in my off hours, I play video games. I really do enjoy.
Anybody play video games? Anybody?
Playing Zelda or, yep, video games are awesome. And I love traveling, going out and just seeing new places and meeting new people. So it's great.
That's really fun. So I'm thinking a little bit about the electrical engineering. That had to do with kind of taking things apart and putting them back together. Yeah.
Right, understanding.
Yeah. That sounds really interesting too.
It was good. It was fun.
Yeah. That's good. I imagine a lot of you like to do that too, kind of tinker with things and take them apart. So, you may not be sitting there thinking, I want to study electrical engineering, but think about the fact that if you like tinkering with things and taking them apart, that may be a good career to consider.
Yes, there's mechanical engineering too, which is, it's more of the mechanics and hardware. And of course, there's computer science, which is also really, it's cutting, right now, NASA, it does a lot of computer science. Because that's how we get our messages out, and that's how we collect the data, and then we analyze it. So there's a lot of programming opportunities if you like that as well. So
very good point. Very good point. Yeah, that's great. Okay, so let's get started with your slides.
Okay.
I think, yeah.
So before we go on to the slides, I did want to
Oh, we want to show a
video.
video.
Yeah,
Yes, we do.
It's a
Yeah,
3-minute
yeah.
video that talks about
Mhm.
ozone, stratospheric ozone, and SAGE.
When compared to other stars around the universe, our sun is really not that big. In fact, by universal standards, our sun is listed as a small to average size star. But for us here on Earth, the sun is the perfect size and distance from us to sustain life as we know it. The sun, for all its benefits, daily rains down on Earth dangerous skin cancer-causing ultraviolet rays. We can protect ourselves with a healthy dose of sunscreen, but nothing works as well at protecting us from the sun's ultraviolet rays than the Earth's own ozone layer. Earth's stratospheric ozone layer is a belt of naturally occurring ozone gas that sits 10 to 30 miles above Earth and serves as a shield from the harmful ultraviolet radiation emitted by the sun. This layer filters out harmful sun rays, including a type of sunlight called ultraviolet B. Exposure to ultraviolet B has been linked to cataracts and skin cancer, and has also been linked to crop injury and damage to ocean plant life. Clearly, it is vitally important for all life on Earth to assure that the ozone layer continues working optimally. Researchers found a large hole in the ozone layer over Antarctica. Human-driven activities were changing the ozone layer. It found that the main culprit for this rapidly diminishing ozone layer was a man-made substance called chlorofluorocarbon, or CFCs. Since the original discovery of the ozone problem, NASA has led the world in monitoring the ozone layer. Here in this clean room at NASA Langley, researchers are preparing to launch a science instrument that will undoubtedly affect the lives of virtually everyone on Earth, even though most people know nothing about it. It is called SAGE-3, which stands for Stratospheric Aerosol and Gas Experiment, and its main goal is to monitor the Earth's thin protective ozone layer. Researchers have found that even a 1% change in ozone layer can lead to a 4% increase in skin cancer.
Human activity on the planet has gotten to the scale where we're impacting our environment. It's our responsibility to keep track of the effects of those impacts.
Obviously, the ozone layer is something that protects us from UV radiation, but there's a lot of effects for the average citizen. They may not see it directly, but ultimately the data that comes out of something like SAGE drives policy decisions by the U.S. Congress.
This team is working hard to continue the tradition of excellence left by other SAGE missions. Their efforts will undoubtedly affect the lives of all of us back here on the planet.
Okay.
So I hope you all were able to see that. It's a really good video about why it's important to do what we do. I can now go ahead and go through the slides. Okay. So
Okay.
Okay, so this first slide, it just essentially shows what, pictorially, it shows what the video was saying. It says that the sun, and then we have this ozone layer that's in the stratosphere. You see that the tropopause is that dotted line, and it separates the two atmospheric regimes that we talk about a lot. And most of the jets fly either just below the tropopause or at the tropopause when you're flying on a jet airplane. So the ozone layer is just above that we're talking about today. It's stratospheric ozone. It's our sunscreen protection for the planet. And then you see that volcanoes, when they erupt, actually do erupt high into the atmosphere. And if there's a really strong atmospheric thunderstorm, you'll see that also gets through the tropopause into the stratosphere. And both of those can affect the ozone layer, either locally or globally. So in the troposphere, we have all the pollution, we have cars and burning and fossil fuels. A lot of that stays in the tropopause or the troposphere and doesn't normally get through the tropopause, but they can occasionally get up into the tropopause and affect the ozone layer. So
So the tropopause is where we're living. If you haven't picked up on that, look down at the bottom, because I know we have some younger ones with us. Yes. And for the kindergarten students and some of the younger students, that bottom layer where you see all the factories and the cars, the tropopause, is what we're walking through every day.
Troposphere, yes.
Yeah, excuse me, I said it wrong. Yes, yes. There's my 2 mistakes for the thing. I'm done now.
So the troposphere, so there's 2 types of, there's ozone that can happen in the troposphere. That can also, that's a very negative effect. It's not, we don't want a lot of ozone in the troposphere, but we do want a lot of ozone in the stratosphere, because that's our, when it's up that high, it protects us from the UV radiation, just like the video was telling us.
So good ozone and bad ozone,
Yes.
right? Good when it's up in the stratosphere,
Yep.
not good when it's down in the troposphere.
Absolutely.
Yeah.
All right, so the history of SAGE, we have a very long-term record from the 1975 all the way through to today, where we take measurements. We've taken measurements of stratospheric ozone. So, we started with SAMS in 75, we have SAGE 1 in 79, we had SAGE 2 it was a long 20-year record there. That was in the 80s and 90s. And then SAGE 3 went up on Meteor. There were 3 instruments that were built all at the same time. And we sent one up on a Russian satellite in 2001. And then, of course, the second one is up on ISS now. And so this is just about ozone. It shows now the fluorocarbon. I'm sorry, I call
I'm passing it on. I'm sorry.
It's really hard to say it. I just say CFCs because CFCs.
Fluorocarbon. We'll master that together.
The CFCs, you can see the chemistry above. Essentially, it's chlorine plus ozone. It destroys the ozone and makes ClO and O2. And then it can also destroy the there's a one single molecule of oxygen, and that also gets destroyed. It just makes more O2. So chlorine in the stratosphere is a ozone destroying chemical. So we try to avoid putting chlorine up into the stratosphere. So when we did these experiments, when we found the ozone hole and we did these experiments way back in the 70s and 80s, we realized that it was CFCs, and CFCs were in everything. They were in our air conditioning, in our cars. They were in aerosol spray cans for, when people want to put hairspray in their hair. They were everywhere. And so when the science community informed the world that the CFCs were destroying our sun protection, our stratospheric ozone, they convened a Montreal Protocol. It was a conference of all these scientists and world leaders. They got together and they talked about how they can stop putting CFCs in the atmosphere, and that if they didn't, you see his model at this one picture, it shows that if they didn't, there was a model that showed that we would lose all of our stratospheric ozone by 2064. That's not too far away. It's less than 50 years from now. So they made a decision. They were policymakers, and they made a decision to stop producing CFCs and stop releasing that into the atmosphere, and that became the Montreal Protocol. And that's what SAGE is going to be doing into the future. And I'll show a picture of what SAGE actually looks at. But SAGE is now going to be monitoring the atmosphere and seeing if that Montreal Protocol worked. Did we actually stop the ozone destroying, the ozone depletion in the stratosphere by getting rid of the CFCs? And there is some evidence that that is indeed what has happened, that our ozone is recovering. So what SAGE does is we look at the sun and the moon primarily through the limb, of the atmosphere. We call it the limb, but it's just the atmosphere. As you can see, we just have a straight line of sight through the atmosphere to the sun, and we do a vertical profile measurement where we're looking at ozone all through the depth of the atmosphere. And then we also have the second science collection. It's called limb scattering, where we actually just look at the lighted side of the atmosphere and take measurements, and we can get some ozone measurements from that as well. So we can we get as much coverage as we can by doing these two different techniques.
There's one thing I want to point out while we're here, if I could,
Sure.
Marilee. So if you're looking, the ISS is, and the instrument is what's right up above the Earth there, and that thin little layer is the atmosphere. Don't miss that. We think of the atmosphere as this vast place of this area above the Earth, and it's very, very thin layer surrounding the Earth.
Yep, it's we have to keep it. We have to monitor it and protect it. So the SAGE instrument is here. It shows there's many components to the SAGE instrument, but what you'll see here is a sensor assembly. That's where we actually collect the light. So it's like a camera. It's a spectrometer, which is it breaks up the light into all these different wavelengths over from about 400 nanometers. Some of you don't care about this, but 400 nanometers to
It's important to know. The
1,000.
units are important.
Yes, they are important. 400 nanometers to 1,000 nanometers. So it just breaks up the light across the frequency like a rainbow. And from that information, we can actually see the ozone and the water vapor and the aerosol, because those things actually absorb different frequencies of light. And if that light's missing when we receive it, then we know that it's being absorbed by a certain amount of ozone, aerosol, or water vapor that's in the atmosphere. So it's essentially a camera it's a wavelength camera. That's what a spectrometer is. So that's what that gold, that's the sensor assembly that is really the heart of the instrument. And then you'll see that we have a hexapod, and that's for pointing, because it's very important to know where we're pointing when we take these pictures. So we use the hexapod to point us in the right direction in the atmosphere, as well as to understand where we are pointed. So that's an important mechanism. And then we actually have some controlling boxes. We have the instrument controller electronics, that's the ICE box. And then we have the hexapod electronics unit, which also controls our pointing, which is the hexapod. And so we also have two other experiments on there, they're kind of independent, but they're useful for us to have. And one is a contamination monitoring package. We're up on the space station, and most people would think that it's a very clean environment in space, and it's really not, because there's this cloud of debris that actually is around the space station that could cause contamination to our optics. Our really concern is to make sure that the optics stay as clean as possible, so that we get all the light that's coming through the atmosphere into the instrument. And if it gets gunked up with some sort of material, like fog, it fogs up the window, then it will change our science results. So we use this contamination monitoring package to find out just how much contamination we're getting at the optics at the SAGE instrument. And it's kind of interesting that it can get a little bit gunky up there. So far, we haven't had any problems with the optics, but we're definitely monitoring.
It's something you need to watch. You don't want the lens, if you will, to be dirty.
Yeah,
if you think of a camera, yeah.
And then we have a disturbance monitoring package, and that tells us just what kind of vibrations we're getting as we're taking science, because this ISS is a large structure, and things do vibrate on it, and that will change where we're pointing. I mean, if just a little bit of vibration can change where we're pointing by kilometers. So we monitor the kilometers in the atmosphere. So we monitor the disturbance that's happening at SAGE, and then we can take that information and back out our pointing information from the science data, and so that we know exactly where we're looking in the atmosphere for the aerosol, water vapor, or ozone amounts that we're looking at. And of course, there's a couple of other things. There is the IAM, which is the brains of the whole package. I mean, that without the IAM, we wouldn't be able to operate. So it's the computer essentially. And then we have the express palette that all of that sits on. And then this is the instrument as it was in the clean room. Looks very much like the conceptual picture. That was years of engineering. And
how many years was that? That's interesting to talk about. Yeah, it was development and engineering.
So it was built by Ball Aerospace in Boulder, Colorado, and that was done in 1999. And that took like 3 years to build it. And then when it was put in storage for 10 years, and then when we brought it out of storage, it took another 7 years to take it out of storage and modify it the way we needed to for the ISS, and get it up, get it ready and launched. So I mean, it was a long project.
And it's
Worthwhile.
okay that things take, that's right,
Oh, yeah.
worthwhile. Yes, that's an important thing to remember, that sometimes science takes a while, but all that time is very worthwhile.
Oh, yeah, absolutely.
Yes.
In that time, we got the instrument configured the way we needed it to be to work on ISS, and we completely characterized it. So we know exactly what we're getting when we're up in orbit.
Great.
Okay, so this is an additional piece of hardware that needed to be put together so that the instrument is facing nadir. When I say nadir, it means it's looking straight down. Well, it's pointing straight down to the Earth, because the ISS is an interesting platform in that there are different places you can mount things to, and unfortunately, the mount that they gave us, the real estate, we actually call it the real estate on the ISS, was not giving us a nadir view. So we had to build this extra piece of, as an L bracket essentially, so that we would have, so that the instrument would be pointing down towards the Earth, so we can look through the atmosphere as we're locking on the sun and the moon. And so that's the picture of that. I mean, actually, it turns out that was quite a job engineering-wise to put that together, because you have to really interface with the ISS people as well, who built the actual platform. But they did a great job. So this is everybody that worked on this project. Well, almost everybody. You see that this took a marching army of people to get this engineering
teamwork
development task. Yes. You become a family over those 4 years, so 4 or 5 years of working on this towards the end. And that includes this analysis people there, people that do our finances. You know, the whole, it's everybody that is involved in the project, you know, to make sure that we get funding going forward, as well as the engineering and the science. So we launched on February 19th at 9:39. It was spectacular. They broadcast it on NASA television, so it was great to have this. It was delayed a day. We all were worried.
Yeah, weather can come into things. And
So finally, the next day they launched it, and it was a very happy day for everybody. So this is what we looked like when we separated out of the Dragon. We launched on the, it's called a Falcon 9, which is from SpaceX, and this is the Dragon portion of it, which is where the hardware, you know, any kind of supplies that go to the space station is in the Dragon.
Okay, right. So let me say a few things there. If you remember the shuttle that used to take things up to station,
yes,
SpaceX is now launching a vehicle called the Dragon that is taking things to space and taking it to the ISS, excuse me.
Yes.
So that's what we're talking about here. Yeah.
Yeah, it's just it's we don't have the shuttle anymore. We have three ways of getting hardware up to the station, or getting supplies up to the station. And right now, SpaceX, the Falcon 9 Dragon, is really what they use right now. And so there we are sitting in there. You can see us sitting in there. There's the top two components is SAGE and the MVP. And then there was a third instrument that's at the bottom. And that also went up there on that trip as well. So here we are. They grabbed the Dragon, and they brought it to the space station. That was I think it's 2 days, or it looks like it's 4 days later. So it takes time. Yeah. So everybody had to be patient on the ground. You know, we worked for 7 years to get this instrument up, get this instrument ready, and then we all had to just sit there and wait while the station grabbed it. And so then they took those two components that were in the Dragon from the 2 pictures ago, and they had to use a robotic arm, and the whole thing was done by robots. There was no astronauts helping us or anything else. It was all done from the ground by a robotic team, and I'll show a picture of them later. So, you know, those are just people that just manipulated this arm and took us out of the Dragon and then installed us on onto the space station, on our real estate on the space station.
That's some high-tech remote control.
Yes. So I'm going to go ahead and show a video now of it. It's very quick, 30-second video that shows a very fast pace of the entire operation, the robotic operation. We actually got to watch that live.
Yeah, this doesn't have audio with it, right? So you can talk over it if you want to.
Right. So it's just that I believe this took 5 days in actual time, and you can see that it's just this robotic arm that is just you know, moving all these pieces around. And then what's really cool is the arm is actually, it disconnects and moves over, and it's like a centipede or one of those little worms, you know.
This looks like a video game to me, right? Talk about video games.
Yeah. Somebody had to put this together. This is all model. This is it was a really amazing thing to watch in real time.
Yeah.
So I enjoyed seeing, you know, all that work, that engineering work and robotic work that they did, and
having that all come together.
And and getting us where we needed to get, you know, where we needed to go on the space station so that we can get the science that we needed to get. So this is where we're located. It's on, there, you can see the space station, you can see the solar arrays, and there's just this one section called ELV4. And so that's where we're located, and you can see that they had to put the L bracket there, and then they mounted us to the L bracket so that we're facing down towards the Earth. And this is I'm not really sure what this is. Oh, that's the L bracket right there. Okay.
Okay. Piece of hardware that holds it on.
Yep. So this is us actually on the ISS, or installed there. And you can see the limb of the atmosphere, or, you know, that thin atmosphere right behind us.
It's a great picture of how thin the atmosphere is.
Yep. And that's what we're trying to get a vertical profile of, is just moving through that tiny little band. So in the front picture here of all the people in blue, that is the robotics team. They were the ones that did all the work to take us out of the Dragon and get us installed where we needed to be. And it was incredible feat, and they did a great job. So I mean, if that's something that you're interested in, you can also, you know, go in that direction, right? Because that's both computers and animation and modeling, and, you know, it's amazing. So the picture behind on the top there, that is everybody that does the mission operations. It's science and mission operations. So we have every day we have a command window, so we can actually talk to our instrument every day, and the people that are in that top picture are the people that do that job, monitoring the instrument daily, and if we need to command it or we need to send up software, we can do it daily. And then of course we get science data coming down daily as well, so we actually look at that and make sure that everything's operating as we expect, and just getting a first look at the science data that's coming back to the Earth from the SAGE instrument. So we powered on, it is just a quick history, we powered on March 16th, and we got first light at that time. So we haven't been on very long. It's just been since March. And then this is just an example of what we see from what we call a telemetry stream. It doesn't really show you the science. This is just showing you the mechanisms on in the scan head collecting the data. So we actually caught the solar eclipse where we're looking through the atmosphere, or just above the atmosphere, and we're looking at how the moon was actually, you know, cutting off our light source from the sun. And you can see it by those weird little, you know, dips in our signal that slowly go away. The blue line is the scan mirror. So the scan mirror, you actually have a scan mirror that's scanning across the sun. It just moves, and it moves in that sawtooth fashion. But you can see that as we're scanning, you know, as we're following the sun as it moves, we actually caught the eclipse and how the moon finally left. We get a very clear signal towards the end, and then this is actually a sunset. So we actually, at the very tail end, you see we're losing some light because it's getting absorbed by the atmosphere as we're looking at the sun as it sinks into, you know, as it sets through the atmosphere. So it was just kind of really cool that we actually got to see this, you know, in real time.
A different representation of the eclipse.
Yes, absolutely. So at that point, I'm ready for any questions. And if I didn't explain something or said an acronym that
right, we love acronyms at NASA. We're all about acronyms. Yeah.
So just let me know.
Well, thank you. And let me remind you, if you are watching, I know Kelly's watching as well. I don't think I mentioned that earlier. So Gina, Kelly, or Elena, if you want to send in questions, I do have my email here, and Caroline is watching as well. Sarah, is your class still connected? I know you had to leave a little bit early. If you are, I'll let you go first on asking questions. There they are. All right, is there anything that you'd like to ask? Sarah, is there any question you wanted to ask? If not, I have a question for you. So if you have a question, go ahead and ask it. But what are you studying with the Globe protocols? What will you be collecting data on? No. Maybe turn your speaker off. That might, yeah. We're hearing you twice. Oh. Well, that sounds nice. That's very interesting. All right, we'll try it once more, and then if not, we'll come back to you. We'll let Karen. That's why I'm so happy to have Karen connected. Question into me as an email. You have my email, and Dr. Markley will answer it that way as well. Sure. So, do you want to try once more, Sarah?
We'll just send in questions, I think.
Yep, we're sounding good. Go ahead.
Yeah, I don't think this is.
You want to ask the question? Okay. Yeah. If you'll turn down your speakers, I don't think we'll get the feedback. But I hope you can hang on a minute. I'm going to go to another school just so you can work that out. So turn down your speakers because what we're hearing is the speaker noise coming back in. So let's go over to Tyler's class. Tyler's students, if you want to unmute and if there's any question you want to ask. And if not, I would like you to tell Marilee about the research you're doing with Globe.
Where's that?
So please tell us who you are before you start talking. That would be very helpful. Thanks. And make sure you're unmuted. I think Karen might be doing that as well.
Oh, can you hear me?
I can hear you, Tyler. It's good to see you again.
Yeah, I'm Tyler Ivanoff. I work here as I'm a tech person in a school, and I'm studying to become a teacher. And thankfully, we've got some awesome teacher. This guy is our English high school teacher, and he allowed me to use his class to work with these seniors in Shishmaref school. So we've got our senior class here, and we just started our group meetings for youth leaders, and we'll be going over some climate change stuff. We're going to focus a lot on climate change and also on wellness, but I think we might be doing cloud observations or something simple to introduce kids to climate change. But we have a student here that would like that had a question. Introduce yourself, Jeremiah.
Hello, I'm Jeremiah Aitanuk from Shishmaref, 17 years old, and I have a question about that mechanical arm. How did you guys control it? Like, did you guys see it digitally or with the video? How did you guys know where the movements were? Or, yeah.
So yeah, I know. I'm thinking, like, was there a little remote, like a Xbox controller?
So I'm gonna let Kristen.
All right.
Knows about
Welcome
that.
back, Kristen.
Yeah. So that's a great question. Oh, sorry.
Just move it over. Yeah.
So that's a great question. So how the robotic arm works is that it's controlled from Johnson Space Center in Houston, Texas. And what they do is it's kind of like a really intricate dance. They have to first choreograph it. And so they write out a binder full of documents, full of pages of move this piece of the arm this many degrees to the left or south or north. And so they really intricately plan it out, knowing all the measurements and having a model of the space station to work with and having a model of the instrument payloads to work with. And then once it's all been planned out, then they practice it. They simulate it a few times on a computer, and then they actually go through line by line from their plan when they're going to actually do it, live for real, and they have the chance to, like, oops, maybe we're like a little too far there, so we'll back it up for a second and try again. And it's controlled from a computer using, just using the keyboard and typing commands in. So
wow, so that would be similar, I think, to writing instructions. Have two students back to back. That's an exercise I've seen done sometimes, and then you have to tell the one student how to get to another point in the classroom, and you get to see how that's playing out, right?
Right, exactly. And so that's how the arm is operated. So that was a really good question.
Did that answer your question, Jeremiah? Thanks so much for your question, first of all.
Yeah, thanks. I know.
You are most welcome. Yes. So glad to be connected with you. All right, let's switch over. I'm not sure if Sarah's class had to leave, but I know they have to leave early, so I'm trying to give them a chance to ask questions. Do you want to try that once more? Oh, that might have been them that just dropped off. Okay. Karen, if Sarah's class is still there, if you'll unmute them so they'll be ready, we'll come back to them. Let's go over to Julie's class. In fact, it's two classes, right? Dot Lake School and Tanacross. I think I'm getting that right. We'll see. Okay.
Oh, right there.
Do you have any questions? And if not, tell us what you're going to be collecting with the globe data.
Yes, you ask one.
Hello.
Hi.
Can you hear me?
Yes.
I can hear you. Can you tell us your name?
Yeah, I'm Galen Isaac, teacher's aide. I was wondering, this is an engineering question, actually. I think Ms. Roel, did I get that right?
Yes. It works.
Well, doctor, I was wondering what non-freezing. What?
I said we're going with Marilee. That makes it simpler.
Yes, Mary Lee, there we go.
Okay.
What non-freezing or antifreeze lubrication do space instruments use in that cold of an outer space up there?
Cool.
I only know it's incredibly special.
Yeah.
So they
great question.
So I know that in a lot of the things that they try not to use a lubricant, they try to design it so, like with Teflon, and Teflon is it already is very free moving. So a lot of parts that need to move are made with Teflon. So you don't need a lubricant because of the freezing issue. The solar rays do have a lubricant because they move so they can follow the sun. But they've done a really good job of making sure that it will last a very long time. I couldn't tell you what it is, but yes, the cold of space is problematic when it comes to lubricants.
It's a harsh environment
Very
to operate
harsh,
in,
yeah.
for the ISS in general. So great question. Did that answer your question? Do you have any follow-up question to that?
Yeah, actually, when you do send instruments up into space, do shuttles pierce the atmosphere or ozone?
So I've actually had people ask me that question a lot, and no, the atmosphere is it's like water. So when it's just a very light, invisible water source, essentially. I mean, think of it that way.
It's a fluid.
It's a fluid. That's what the atmosphere is. So as you send something up through the atmosphere, just as if you dropped a stone into a lake, the water fills in behind it, and so that's what happens with the atmosphere. So yes, you are. When you send a rocket up, you are putting propellant into the atmosphere, which is pollution. And so you are adding to the problem, but it's a very small amount compared to everything else that we do from the Earth, factories and cars and, burning fires and stuff. But as far as leaving an actual hole, no, it's not a piece of paper. It's just like, it's a fluid, just like when you have a bathtub, it folds in on itself and fills up that void as the rocket goes through it.
Great question. That's
Yes,
a really
I've
important
actually
thing to
heard
keep
that
in mind.
question a lot.
Yeah,
So-
yeah. And keeping in mind that the atmosphere is a fluid is very important, because when you think about the way that air moves around objects, it's a very fluid movement because that term is used for that. That's
yeah, you can kind of think of it as it's a fluid that has it's stratified. So just like, have you ever heard of thermoclines in the ocean, where there's the temperature changes from one zone of the ocean to, you know, either above or below it? It's the same way. It's gravity just makes it easy to have these kind of layers. And so it's still a fluid, but there are layers to the atmosphere, just like there are layers, thermoclines in the ocean. So, you know, we have the troposphere, we have the stratosphere, we have the mesosphere, just layers. But essentially, in that layer, it's a fluid, and you can actually have movement between the layers, which I showed you with the volcanic and the, you know, really deep thunderstorms can actually break through those layers of atmosphere. So,
excellent. Great questions. Thank you. Thank you very much. All right, let's go to Eagle Community School. Marilise, does anyone at your class have a question?
Yes, Jessica is there. She's going to ask a question.
Okay.
Go ahead, Jessica.
How long does it usually take for the hi? How long does it usually take for the sage to get into the right spot in space?
So when you're saying sage getting to the right spot in space, are we talking about pointing through the atmosphere, or are we talking about ISS related?
Yeah, what do you think?
So it took a couple of days for it to get from the ground to the space station.
Right.
So that was a couple of days, and then it took a couple of more days for them to take it out of the trunk and install it onto the space station. So now it's permanently affixed to the space station, and it is and the space station orbits. And the space station orbits, help me, how many times a day?
It orbits. It's every 90 minutes, so it's 16 orbits a day.
Okay. So for SAGE to make its measurements, it needs to be seeing a sunrise or a sunset, and that happens
twice a day.
Twice a day.
Or twice in orbit, which is 32 times a day.
Okay. Yeah. So to answer your question, a couple of days to get to space, a couple of days to get on its spot on the space station, and then now that it's on space station orbiting, it gets to the right spot to make its measurements on the space station 32 times a day. Is
Right. Yeah, every 45 minutes we can get a sunrise or a sunset.
Sure.
Okay, so we can measure every 45 minutes.
Yes, it does.
Yeah. Data collection.
Yes, it does a data collection every 45 minutes, and then you have additional. You can do a lunar, and that's wherever the time the moon is in view on the dark side. So that could be every 20. You know, you do a sunrise, and then you do a sunset. Then you do a moonrise, whichever one, and then you do another solar event, a sunset.
Did that answer your question?
He
It's not.
Ask again. Maybe we misunderstood. That was great information, but please do ask a follow-up question if that's a good idea.
You want to go answer that?
Okay. So how long did it take? I'll quiz you. How long did it take for the Dragon to get from Earth up to the ISS with SAGE in it? Anybody there at Eagle Community School? I'm putting you on the spot.
2 days. 2 days. 2 days.
Good. Before you go, tell us what you will be collecting. What are you collecting GLOBE data on?
Hydrology.
And we're going to start in atmosphere and clouds.
Okay.
That's very cool.
Aerosols eventually. We're going to try to do aerosols with the chemistry students.
Yeah.
That's very cool. So I know there are some great activities on the SAGE 3 website on aerosols.
Yes.
So that would be a great place to look for some classroom activities on aerosols. Yeah.
Thank you. That'd be great.
Awesome. Okay, let's go over to Watershed School. And I believe Chastity is there, and so is Chris. I bet there's a few questions there.
Yeah, we got a few. So
okay.
All right.
Please tell us your name so we know who we're talking to.
All right. Hi, my name is Josie.
I'm in 5th grade at Watershed in Fairbanks, and I was wondering, we couldn't hear you very well here, and so I'm not sure if you covered this already, but how long did it take to develop SAGE?
That's a great question. So it was a 2-stage development process. One was actually where we went to Ball Aerospace in Boulder, Colorado, and they actually built the instrument for us from, pretty much from blueprints all the way to finally getting it to final instrument. Probably took about 6 to 4 years. So the actual build of the instrument, where they actually had hardware being made, was about 3 years long, but you still had the 3 years before that of development. And you had to also develop the sensor, which is the detector, which is really essentially the spectrometer, the camera. So that was a long process. And I was there for the last 3 years of that. So in 88 through 2001. And then when it got put into storage, they had to bring it back out of storage 10 years later, and it had to be a lot more development because they had to make it ISS ready. And that took, 7 years? It was 7 years. So a total of 10 years actual hardware with that big break in the middle. So this is a long-term project. When you work on this, it takes a while to put this together to give you what you want, but we get great science from it in the end.
And can I just add, the reason that it takes so long is because we don't want to spend all this time and all this money and then have it get up there and not work.
Yes.
And so there's a whole process of designing it and building it and testing it, and that's just the test version. And then you do it all again when you build the flight version, the part that's actually going to fly. And then you integrate everything all together, and then test that again. So it's always test to make sure that it's going to work when it gets into space, so that we can get the data that we really need.
And that's how engineering's done.
Yes, it's the engineering design process. For sure.
Great. Thank you.
Question.
You're welcome.
Another question? Watershed School?
Hi, I'm Talia, and this is Devin.
And we were wondering how many movements the robotic arm made.
Oh, that's a really good question. I mean, I don't know the answer. I don't want to pretend to guess. Hundreds, if not thousands, of small movements.
And each one of them had to be a step.
Yes.
If you think of the written log of steps.
Because the arm isn't just one piece. It's kind of, think of it as like an arm with a hand with fingers. So one part might move, but then this part might so the arm might move, but the hand might move a different direction, and the finger might need to move too, or maybe just the arm part or just the finger part. So it's really a complicated robot. That's a good question, and I can try to find the answer and give it to Bonnie to send to you. But yeah, that's a good question.
That's
a lot of movements.
And is the word articulated what's used for those kind of robots?
It sounds right.
Because I've heard that term somewhere. So we'll look that up as vocabulary. Because when there's parts within parts, I think that's a term that comes into robots like that. So anyway, just building vocabulary as we go too. Did that answer your question?
Yeah.
Thank you.
Yeah, you're welcome.
So I have a question and then I have a comment. My name's Emma, and what type of robots did they use to build the thing that Sage?
Okay, so Sage wasn't built with robots. It was all people, and it was, they machined the parts and stuff, but the actual Sage instrument was all put together by human beings, technicians, and then crazy testing, lots of testing. And then the only time we actually used a robot was pretty much to install it on the space station. And, that was all Johnson Space Center. That's they control.
The robotic arm is called, it's called Canada Arm too. It's an arm so the space station is an international partnership. And so the arm was designed and built and kind of donated by Canada. And then the hand part of the arm is called Dexter, which is an acronym. I forget exactly what it stands for, but it's, dexterity. So, so it's just a big mechanical arm is the robot that was used to install.
My comment
Go ahead. I was going to say, do you have a follow-up question?
My comment is that my uncle works for NASA.
Oh, cool. Awesome. Well, that's close to home for you then, huh? Do you know which center he works at?
He works in Russia, so.
So he must be working for Johnson then. Johnson, because they send a lot of people to Russia.
Yeah.
Okay. That's great.
Very cool.
That
That's
was a
very
good-
cool. Thank you.
Thank you.
Hi, my name is Mira, and I have 2 questions. When did you guys want to start being scientists?
So I wanted to be a scientist when I was in junior high. And then, of course, with the eruption of the volcano, Mount St. Helen, that really kind of intrigued me. I did take the long way to get there. I went to engineering school first and got my electrical engineering degree. But I mean, in a way, it's still, I mean, engineering is just it's such a subsection of science. So, I mean, but yes, that was way back in junior high school.
Mm-hmm.
And the other question is, how does Sage get from Earth to the moon?
To the moon?
So it went to space.
Yeah, so SAGE is actually installed on the space station. So, right, it's orbiting the Earth. And so what it does is it actually looks at the moon, the light from the moon through the atmosphere and the light from the sun through the atmosphere. So it actually is it's still very close to Earth. It's still
less than 400 miles, right?
400 kilometers, right?
Okay.
400 kilometers
Gotta get the units right.
above the Earth. So yeah, so it just uses the light from the moon and the sun.
And how we got it to the space station was on that SpaceX rocket that Marilyn talked about earlier. So a rocket with a unpressurized trunk at the bottom of it, and with all the instruments inside.
Yeah, so it's a Falcon 9 and the Dragon. We were installed in the unpressurized portion of the Dragon, which is the very top capsule where they put all the supplies. So that's how we got there.
Good question. So it's looking at the moon, but it's actually on the ISS, which if you took your hand and you went, that little layer of water vapor that's now above your hand is about how thick our atmosphere is above the Earth.
Yep.
So, and you can look up someplace that's 400 kilometers from where you are in Alaska and get an idea of the actual distance that is. But it's very, very thin, and ISS is actually within that. It's just at the very edge of that.
Yep.
Thank you.
Thank you.
You're welcome.
Hello, I am Liam, and I was wondering, how hot is the biggest sun?
Oh, that's a good question. I don't know the answer to that. Yeah.
Which is neat. You know, when you're studying something, I want to point out, when you're studying a particular area of science, there's a lot of areas you need to look up and learn about outside of what you're studying. So,
because I mean, our sun is really, it's hot. I mean, they have the thermosphere. I think they said it was 35,000 degrees. And, you know,
that's hard to even imagine.
I know it is,
Yeah.
but when you actually take a measurement, it's like underneath that, it's 7,000 degrees. It's still really hot. We're talking Fahrenheit here, 7,000 degrees. So
thank you.
Yeah,
That's a good research question.
Yes.
You need to report back to us on that after you do some research.
Thank you.
Thank you.
Hi, my name is Emily. I have 2 questions. What kind of fuel does SAGE take?
That's a good question. So SAGE doesn't actually use fuel. We're very lucky in that we designed it so we don't have, fuel is usually a consumable, so eventually you will run out of it, and then that's when your experiment dies. So we didn't design it for that. We wanted to have this, if we can get this instrument to operate for 20 years, we'll be very happy. So we don't want any kind of fuel or expendable consumable. So what we do is we actually attach to the space station and we use the electrical grid that's on the space station. So all those solar cells that you see collecting light and
all of these behind us,
turning the
Right.
the light of the sun into electrical energy, and they have batteries. And we are powered from that grid. And as long as they are operational, we'll get power for SAGE. So hopefully will last for a very long time.
And will SAGE like run? Can it run into planets or anything?
So let's think about this. It's in Earth's atmosphere, right? It's right above Earth in Earth's atmosphere. So is it in danger of running into any planets if it's right around Earth's atmosphere? What do you think?
Just us. It can run into Earth.
Yeah. Now, there is another topic that we might need to be concerned about, and that's space trash.
Yes.
There's a lot of debris. Maybe I shouldn't use the word trash. There's a lot of debris that is in space, and we always need to worry about that with any object that we have up in.
Yeah. So if there's a big enough piece of trash up there, they will actually move the ISS. They have propellant on the ISS, but they replace that every time they put a resupply mission up. They actually send more fuel up there. But when they see something happening, or they might possibly be hit by something, they just move the space station out of the way.
Excellent. So. Yeah, right, because it's not, good question, it's not in danger of being hit by another solar object. However, it could be in danger of objects that are floating near the Earth.
Yes.
Yeah, great question. Thank you.
Thanks.
Okay, so at this point, I'm just going to let questions come in from the audience who's watching. So Caroline, if you'll share with us, Caroline's down there in the left window for me. Hi, Caroline.
Hi, guys. I have a question from Gina, who is using the YouTube chat to ask some questions. And she asks, how do teams such as SAGE come together? Are they handpicked, just NASA people, or are they from around the world? And one more question, how many women were on the team?
Oh, well, that's a good question, because this really was a well-represented group of people.
A lot of diversity.
A lot of diversity. So how I got picked for this is that I was an electrical engineer, and we have directorates here at NASA. And so there'll be an engineering directorate, there'll be, a science directorate, mechanical engineering directorate. So when the call went out, said that we have a project, I was available. I wasn't on another project. So they said, go ahead and go work the SAGE project as an electrical engineer, as a test engineer. So that's how I first got on the project. And that's what they do. Some people will see the writing on the wall and realize this is a great experiment and they want to be on the project and they'll request it. But usually you're assigned it from your directorate.
Sure. And so it all starts with a project manager or a principal investigator or a project scientist.
Right.
So the top level person in charge of the project gets to kind of pull a team together. And so they can find people who need a project to work on, who don't have any work right now. They can find people who they know that are really good at what they do and they want that person. They can put a call out. So there's a couple of different ways that people can be picked and brought onto the team, but it starts to be organized with a project manager, deputy project managers, and they kind of start pulling that team together.
So this was also a very international project.
Yeah.
The hexapod is actually built by an Italian company. So ESA, which is the European Space Agency, was also involved in the SAGE project, and so we had Italians and I believe some French. It was French representation of Belgium on the SAGE project. And the question about how many women, this was probably one of the best mix of men and women. It was probably close to 40% were women. And that's just because of the makeup of SAGE has also changed. But we also have a lot of contractors. These are people that we hire to come in and do certain tasks for us, because you saw it was a lot of people that made up that team, and I would say probably maybe 50 to 60% of that team was contractors. So it was a great mix. It was, we had a great group of men and women that worked on this project.
And it starts at NASA. So I think part of the question was, are they all from NASA? And so it starts at NASA, and the core team is from NASA. And then, like Marilee said, we hire contractors, we work with international partners and industry partners across the country and across the world. So it's definitely not just, you know, people who are already here at Langley or anything like that.
Right.
And yeah, and women played a key role in a lot of positions on the team. Our deputy project manager was a woman. The mission support or our mission operations manager, she's a woman, Brooke Thornton.
And our quality assurance
lead, yeah, Sudha Natarajan.
Yes.
So yeah, so that's a great question.
And if you think beyond even SAGE itself and into the data usage, because the reason this is important is to collect this data, so then using that data, it's used by many countries.
Oh yes,
You know, when you get back to the Montreal Protocol and that was a joint effort.
And that's a good lead into, we are going to be releasing the science data hopefully very soon, within the next month, but we do have a deadline until at the end of the year. We need to release this to the public, and that is everybody. So it'll be available for international partners and universities. Everybody can look at it and look at the ozone and look at the aerosol and look at the water vapor that's in our atmosphere, or stratosphere, I should say.
Yeah.
That was a great question.
Yeah. Any other questions anywhere? Okay, I see Marilise is leaving. Bye, Marilise. Yes. Okay, so Eagle Community School, thank you for connecting. Yes, that's great. All right, well, if there are any follow-up questions that come to mind afterwards, all of the teachers connected have my email, so send them on to me and we will get you answers. And I hope that as you're studying clouds, or we heard hydrology, I know some of you are studying plants. We actually didn't even get into that.
Yes, that's true.
But ozone is very dangerous to plants in the troposphere. And ozone in the atmosphere can actually, lack of ozone in the upper atmosphere can cause burning of plants, as I understand.
Sunburns. Just like we get sunburn, plants get sunburn.
Plants can get sunburn if that would be a lack of stratospheric ozone.
Yes,
yeah,
absolutely.
Yeah. Wow, important. Oh, Caroline, I see you back. Does that mean there's another question? And there may be one over at Tyler's school as well. Caroline? No? Okay.
No more questions.
Tyler over at Shishmaref, do you have another question? Somebody in your class?
I'm Jeremiah, and I have another question.
Okay.
What can we do as consumers that produce the ozones to like make less or something, like help you guys out and let you guys do less work? Like,
so I mean, really, it's really about maintaining and understanding the impacts of what we're doing as humans on this planet. You know, as a first world, you know, we have first world countries that are very polluting, you know, cars and, you know, coal burning electricity, and you have other countries that don't really have that infrastructure in place yet, but they're trying to build to it. So really how you know, technologically, it's how we can improve our impact, you know, will improve our quality of life without putting this impact into the atmosphere, you know, and that's really falling on our shoulders to develop technology that is less polluting, but still gives us what we need, you know, for the quality of life that we want. And then, of course, policymakers have to decide, do they want to burn coal to make electricity, or do you want to go with a cleaner fuel to make electricity? Because really it's all about electricity at this point, except for the cars. I mean, we're going towards electrical cars as well, but it's amazing how many cars are on this planet and burning that fossil fuel, which is putting carbon into the atmosphere, which is a greenhouse gas. And so as we move into electrical cars, you still have to figure out how do you make electricity cleanly so that you are doing less of an impact on the rest of the planet. And you know, those problems, people are they're working on them. I mean, as far as that's a huge, big question, and it's going to take a lot of work from people, you know, from countries and technological advances around the world to really get that question answered. And hopefully it'll happen. Well, I'm hoping it'll happen in my lifetime, that we'll figure it out.
When you become an engineer and start working on these problems, that's the kind of those are the kind of solutions.
Yes,
that
absolutely.
Absolutely. And even before you might be becoming an engineer, the data you're collecting. Globe data is put into a database that NASA supports. NASA is a big supporter of the whole Globe project because it allows data to be collected that can be looked at over long periods of time. When we're talking about changes to the climate, we're talking about a decadal change. Decadal goes with the word dime, it's 10. We're talking about tens of years, probably 30 years. So to be able to look at that data over that long period of time is very valuable. So any of the data collection that you're doing, that's a way you right there in your classrooms can help with this by collecting the data and putting it into the Globe database so that it's there to be evaluated.
Yes, absolutely. Because any information like that, it helps policymakers understand the impact, and then they will be, they can push for these changes, that we need to do to make our planet a very long time sustainable, environment. So,
right. Yeah, very good
great
question. Yes, and we're all on the planet. We're all experiencing different levels of impact from climate change. I know you and Shishmaraf are really experiencing high-level impacts. So we need to all, as a planet, be respectful of the impacts that are happening and think of ways to solve that.
Yes.
Chastity, I see your class is still connected, and I know Chris was there with you. We're past time, but if there's one last question or any burning things you wanted to ask, since you stayed on, I want to give you the opportunity to ask a question if you want to.
Calypso? Where is Calypso?
I didn't hear the question, and I'm not seeing you, but I can hear you asked a question.
Large Animal Research Center or station, I think, actually.
Oh, so you're talking about large animal extinctions? Is that what you?
I did say it, but I.
No, Lamlin too.
It would help us if you speak up a little louder. We're hearing you, but not clearly.
That's a once in a lifetime.
Who's waiting over there? Let's see. Is that Tyler's class? Yeah, thank you, Tyler.
Bye.
Okay, maybe Chastity's class. You are most welcome, Tyler. Thanks for connecting. Thanks to the students for those great questions. Awesome. Let us know if there's any follow-up information you need. All right, and Chastity, I'm wondering if maybe there was just conversation in your classroom, but we'll try one more time.
I just wish I could hear them better.
I know.
I think they're just wrapping up. Okay. Well, thank you to everyone who was connected. Thank you, Dr. Marilay. Yes, and thank you, Kristen, also. This was a great session. It's wonderful to be able to communicate with Alaska right here from Virginia. So thanks to everyone. And for now, goodbye.
Bye.
Bye.